In this video, we are going to discuss what are called integrated rate laws and show you how those apply to the kinetic study of chemical reactions. So as we mentioned, there are two types of rate laws. The first type of rate law, often called just a rate law or differential rate law, shows how the rate of a reaction depends on the concentration of the reactants. The other form of the rate law is called the integrated rate law, and it shows how the concentration changes over time. So some questions that we can answer using our integrated rate laws are as follows. So a couple of these would be how long will it take for our initial concentration of a reactant to decline to a certain level? Once we figure that out, we could also answer how much of a certain product can be produced over a given time period, which is often very useful in chemistry. We could also ask what concentration of a reactant will remain after the reaction has been carried out for some time period. And finally, what concentration of a reactant was initially present before we began the reaction. So when we're studying kinetics, we generally look at the change in concentration versus time, and a sample experiment might look like this. If we study this particular experiment or any chemical reaction, we might want to measure the change in concentration of our reactant over time. So here you can see some sample data. We are increasing in time, and as we increase in time, you can see the concentration of our reactant decreases, which is what we would expect. So if we record the time versus concentration, we can use our integrated rate laws to analyze this data. Now, the integrated rate laws are derived from our regular rate laws, and the integrated rate law depends on the overall order of the reaction. So as you can see, a zero order reaction, if you have an overall zero order reaction, it has a rate law that looks like this. A first order rate law would have a first order integrated rate law that would look like this. And a second order reaction would have a second order integrated rate law, and it would look like this. Now for these rate laws, the A sub T, that is the concentration of our reactant A after some time point, after the reaction's been carried out for some time point. K, of course, is the rate constant for that reaction, and that depends on the temperature. T is the time point that we're analyzing. And A sub 0 is the initial concentration of the reactant before the reaction has started. So let's take a look at each of these rate laws and try to study them in a bit more detail. The integrated rate law for a zero order reaction, as we showed you, this is it. And it's written, if you notice, in the form of an equation for a straight line. If the utility of this, writing it in this form, is that if we were to draw a graph where our y-axis, on our y-axis, we plotted the change in concentration at each time point. And on our x-axis, we plotted the time. If we plotted that and our reaction was a zero order reaction, we would get a straight line. It would look something like this. So here on our y-axis, we're plotting the concentration of our reactant. And on our x-axis, we have time, in this case in seconds. So if we plot these two, we carry out the experiment, we collect our data, and we plot the change in concentration versus time. If we get a straight line, then we know that that is a zero order reaction. We can also determine the rate constant by looking at the slope of this line. And if we carry this out and look at our y-intercept, we can determine our initial concentration for our reactant. Similarly, for a first order reaction would have an integrated rate law that would look like this. And if we were to plot on our y-axis, not the concentration at time t, but the natural log of the concentration at each time point. And on our x-axis, we were to plot the time. If we were to plot those, if it's a straight line, which you can see here, then that would tell us that we had a first order reaction. So if we plotted concentration versus time, and we got a straight line, we'd know it's zero order. If we didn't get a straight line, like you can see here, then we know it's not a zero order. We would then go on and plot maybe the natural log of each concentration at its time point. And if we got a straight line there, then we could tell the order of that reaction. Also, if we looked at the slope of this line, we could determine our rate constant K, and our y-intercept would give us the natural log of our initial concentration. And finally, let's look at the integrated rate law for a second order reaction. So let's say we collected our data of time versus concentration, and let's say we plotted the not the concentration or the natural log of the concentration versus time, but we plotted the inverse of the concentration at each time point versus the time, so our inverse or 1 over the concentration at each time point on our y-axis and time on our x-axis. If we plotted that and got a straight line, that would tell us that that was a second order reaction. So let's say we performed a reaction and we got our concentration versus times, and we plotted concentration versus time. If we got a straight line, we'd know that would be a zero order reaction. In this case, though, we don't get a straight line, so we know it's not zero order. We then go and plot the natural log of concentration versus time. If we get a straight line there, then we know it's a first order chemical reaction. In this example, it's not a straight line, as we can see, so it's not first order. We then take our data and look at the inverse or 1 over the concentration versus time. In this case, we do get a straight line, so that tells us that it is a second order reaction. We can also calculate the slope of the line to get our rate constant, and we could also, if we needed to, look at the y-intercept, and that would give us 1 over our initial concentration. So here's a sample problem. Nitrogen dioxide decomposes to form nitrogen monoxide and molecular oxygen. Here's our chemical reaction. The decomposition of nitrogen dioxide is measured over given time periods, and here's our data. You're asked to determine the order for this reaction. So pause the video and at least see if you can determine it, or at least describe how you would determine the order just by looking at this data. How would you determine the order for this reaction? Okay, so probably the best way to do it would be to look at it graphically, as we described earlier. We could take our data, our time versus the concentration of our reactant, time versus concentration, and if we plot time versus concentration, where this is our y-axis, concentration, this is our x-axis, time, if we get a straight line, we know it's zero order. If not, we would look at the natural log of the concentration, and we would plot the natural log of concentration on our y-axis, time on our x-axis. If that gives us a straight line, then we know it's first order. And if not, we would go on and look to see if it's second order. To determine if it's second order, we would plot time on our x-axis and the inverse of the concentration on our y-axis. And if that gave us a straight line, we would know it's second order. So I went ahead and plotted all these. The first one is our concentration versus time. You can see this is not a straight line, so I know it's not zero order. I then plotted the natural log versus the time, and if this is a straight line, it would be first order. It's not, so I know it's not a first order reaction. And then I plotted the inverse or 1 over each concentration versus time. Here I get a clear straight line, so I know that this reaction is second order. If I needed to, I could also calculate the rate constant for this reaction by calculating the slope of this straight line. Let's look at one more sample problem involving our integrated rate laws. This would be a more mathematical type problem. Here we're given a chemical reaction where hydrogen peroxide decomposes to form water and molecular oxygen. We're told in this reaction that it is first order, so we know it's first order, and the rate constant is given 1.8 times 10 to the minus 5 seconds to the minus 1, and we're given the initial concentration. So we're asked, A, what is the concentration of hydrogen peroxide after 4 hours? How long will it take the hydrogen peroxide concentration to drop to a concentration of 0.12 molar? And finally, how long will it take for 90% of the hydrogen peroxide to decompose? So these are all questions which involve time. Any question that involves concentration and time, we use our integrated rate laws for. Now, since we're told that this is a first order reaction, I'm going to use my first order integrated rate law to calculate this. So pause this video and see if you can answer these 3 questions, and then play it again and compare your answers to mine. Okay, so for part A, what is the concentration of hydrogen peroxide after 4 hours? Now, as I mentioned, I know that this is a first order integrated or first order chemical reaction because I'm told that in the problem. So I'm going to use my first order integrated rate law. And what is the concentration after 4 hours? So I'm looking for the concentration at some time t. I'm given my rate constant, I'm given the time period that I'm looking for, and I'm given my initial concentration. So I plug those in. Something that you need to be aware of, though, again, as you see, I put in my units. Please don't skip steps and not include your units. My rate constant is seconds to the minus 1. My time is in hours. I need to get those in the same units so they cancel. So here, I changed my time from hours to seconds. Now, I can just solve my problem, and I get the concentration of hydrogen peroxide after 4 hours of 0.23 molar. Now again, be careful here. This is the natural log, so we need to solve for just the concentration of hydrogen peroxide, not the natural log of the concentration of hydrogen peroxide. And you could also note that the concentration did decrease, which is what we would expect, and the units of concentration are molarity. Now for part B, our question says, how long will it take the concentration to drop to 0.12 molar? So here, I'm looking for a time. Again, I'm going to use my first order integrated rate law. I know the concentration after some time is 0.12 molar. I know my rate constant, T, that's what I'm looking for, and I know my initial concentration. So I plug all that in and solve for time T, and I get that it will take 5.1 times 10 to the 4th seconds for this reaction, in this reaction, for the concentration of hydrogen peroxide to drop to 1.2 molar. And finally, the question says, how long will it take for 90% of the hydrogen peroxide to decompose? Now, for this one, after 90% has decomposed, of course, we have 10% remaining. So the concentration at time t, I took my initial concentration times 10%, and that tells me that I will have a concentration of 0.030 molar remaining, so that I have 10% left, and so my concentration after 90% has decomposed will be the 10% or 0.030 molar. So that's my concentration at time t. So now again, I'm going to use my first order integrated rate law. I'm going to plug in my concentration at time t after 90% has decomposed. I plug in my rate constant. I'm looking for how long it will take. So I'm looking for T, and then again, I use the same initial concentration. Solving for time T, I get T is equal to 1.3 times 10 to the 5th seconds. So that's how many seconds it will take for 90% of my hydrogen peroxide to decompose. So this problem is a good problem. It shows us some of the applications for our integrated rate laws.